Bismillahirrahmanirrahim. So today we are going to I'm going to start by recapitulating the material that we have covered in the last few lectures. Only the practical aspects, the one that matters. And this is the only thing from the past 2 or 3 lectures. We have been covering the proofs. Now I'm just going to give the results that matter. And there are very few. So basically we start by noting that there is x1, x2 up to xn. These are IID normal theta sigma squared. So we start with this sample and now the main thing in doing a good real world application is to find a data set to which this assumption is well matched. And this is something which is not mentioned in conventional textbooks. But the whole game of producing a good econometric model is to find a place where you can put in an IID assumption which is reasonable. Because people don't mention this, so people are making models of all times, because the mathematics works whether it's reasonable or not. So you can take any data set and model it as an IID, and you will get terrible results if the assumption doesn't match. But people do that, and you can find hundreds of publications, thousands, because this question even is not taught. So publications where the data does not match the assumption of IID, and then you do the same analysis anyway. Analysis never tells you that there is something wrong here. So after we start with this IID sample, then I define A equals 1 over n, summation I equals 1 to n. Xi, this is often written as x bar, and sometimes you put an n subscript to show that this is a sample of size n. Now this has the distribution normal with mean theta and variance sigma squared over n. Then there is S, which is summation I equals 1 to n xi minus a squared. This is the sum of squared deviations. This, if you divide this by sigma, or it's often written as the sigma squared chi squared n minus 1, which is also equal to a gamma density with parameter n minus 1 over 2 and 1 over 2 sigma squared. So this is the fruit of all of the labor that we have been doing for 2 or 3 days. Actually, we haven't even done this. We have done the Bayesian version of these calculations, which I will also recapitulate. Now, one very important thing is that A and S are independent. It's very surprising, but true. The deviations from the mean are independent of the mean. What happens is that there is a proof, but it's more complicated than I can explain right now. Maybe we will get to it when we look at the multivariate calculations of these things, then it's easier to see. That's not as important as the fact that these are sufficient statistics. This is very important. Sufficient statistics for theta and sigma squared. This has the common sense meaning that if I know the value of the A and the S, then I don't need the rest of the data in order to do inference about theta and sigma squared. it also has a technical meaning. The technical meaning is that if you look at the distribution of the whole data conditional on A and S, this does not involve the unknown parameters. So the implication of this is that once you have A and S, if you throw away the original data, you can generate new data which has the same distribution as the original data without any difficulty, because the conditional distribution of the whole data given A and S doesn't have any unknown parameters, so you can generate it.
लेकिन जब डेटा हम जनरेट करेंगे तो उसी हमें कंपोजिशन कैसे नोन होगी, किन किन कंपोनेंट्स में देके वो डेटा बना हुआ है, जो डेटा जनरेशन की आप बात कर रहे हैं तो उसकी कंपोजिशन तो हमें नोन नहीं होगी कि डेटा किस तरह बना है।
कंपोजिशन से क्या मुराद है?
डेटा जनरेटिंग प्रोसेस जो है,
डेटा जनरेटिंग प्रोसेस तो है, there is a conditional distribution x1 to xn given A and S. This density, this distribution does not depend on any unknown parameters. It's a known distribution. So this is the data generating process, and that is known, and so we can generate data from this process. So once we know that these are sufficient statistics, then we know that all inference about theta and sigma squared can be based on these two numbers alone, and that is crucial. It means that we can reduce the data into these. Now, what is inference? Well, again, this is very easy. First of all, there are two things that if you have Z1 to ZK IID normal 0, 1, these are standardized normals, then this is just some distribution theory. Z1 squared to ZK squared, this is distributed as chi squared k. We actually proved this. This is one important result. And the second important result is that if I have another variable z in this list, and I look at z divided by the square root of z1 squared to zk squared, this is a T density with k degrees of freedom. This is just the definition. If you take a normal and divide it by the square root of chi squared, you get a T density. So you can calculate what this T density is.
So ये जो x जो हम जनरेट कर रहे हैं ये डिपेंड कर रहा है A और S पे, और A और S completely independent है एक दूसरे से.
हाँ.
इसकी वजह वो ऊपर वाली assumption तो नहीं बनी IID वाली.
हाँ बिल्कुल वही बन रही है, उससे तो पदार्थ तो कोई वही नहीं. A and S come from x1 through xn, so everything, all properties of AS depend on this assumption.
लेकिन सर ये अजीब है ये वाला.
Because you have this data, you can boil it down to these two numbers. These two numbers contain all the information about theta and sigma squared. Everything else is independent of theta and squared. So this is just noise which doesn't depend on theta and sigma squared. So you can regenerate more noise like that original noise. Now, okay, so that's the distribution theory. Now we go to the inference theory. Now we have A, the average, is distributed as normal with mean theta and variance sigma squared over n. and S over sigma is distributed as chi squared, S over sigma squared is distributed as chi squared n minus 1, where S is the, remember that A is 1 over n summation I equals 1 to n xi, and S is summation xi minus A squared. Now for inference in the classical framework, the conventional framework, we need a pivotal statistic. So what we have is that A minus theta divided by sigma, this is times n, yes, times the square root of n. Because sigma squared over n is sigma over square root of n, the SE, and so when I divide by sigma over square root of n, I get this. And then I have to divide by S divided by sigma squared square root. So now this quantity is a T distribution with n minus 1 degrees of freedom. So T distribution is completely known. Oh, and I made a mistake when I was defining it. A T distribution is n01 divided by square root of chi squared n divided by n. Sorry, chi squared k divided by k. In this particular case, k is n minus 1. So it's not just the square root of chi squared, you have to divide the chi squared by its degrees of freedom to get the T distribution. So here we have an extra square root of n on top, and when I bring it down on the bottom, then it will become exactly matched to the T distribution, and so this is a T distribution. The thing here is that the sigma is cancelling. So we have A minus theta over the square root of S divided by, I need an n minus 1 here. And this is chi squared. This is T with n minus 1 degrees of freedom.
So ये वाला step जरा repeat करिए because ऊपर sigma square से
The sigmas cancel. 1 over sigma and 1 over sigma both on the numerator. They cancel. There is some confusion I am having with the n's. It's not important. I mean, with the n and n minus 1, these things will figure out. But there is something that needs to be done here. The crucial thing is that now I have this statistic which has independence. So basically what we do from this, there are only 3 sentences. And see, this is the steering wheel and the brake and the clutch and so on. And now the only thing that we do with this is to make the probability statements. The probability that A minus theta over the square root of S divided by n minus 1 is less than minus 1 is less than plus 1 is about 68%. This is true for large n, because basically for large n, the T distribution is a normal 0, 1. because basically chi squared n over n converges to its mean. The expected value of a chi squared n is n. That's easy to see because chi squared n is the sum of squares of normals. Each normal has value expected equal to 1. So if you add n of them, you get n. So when you divide by n, the expected value of chi squared k over k is 1. So this has expected value of n of 1, and when n is large, then this becomes basically a constant equal to 1. So when n is large, you only have the normal 0, 1 in the numerator. So for large values of n, this will be 68%. For small values, basically you have more uncertainty. So if you want to get 68%, the 1 will become larger on this side, and the tables will tell you at what value of n you have, and so on. So you get 68%, and you get 95% at 2, and 99.7% at 3 for the large n case. And as you bring the n down, you can calculate what those probabilities are, and basically that is inference. That's it.
66%?
68.
1
So what does this mean? Well, at this point, this is a combination of data and parameters. You can invert this to get that theta is basically theta will be between a minus square root of s over n minus 1 times 2 and a plus 2 square root of s over n minus 1. So this is approximately true standard deviation. This will be approximately 95% in large samples, and if the sample is not large, then you can either calculate the probability of this exactly for the 2, or more likely you change the 2 to the right number in order to get the 95% probability. Now the one thing that I'm saying here is that is different from what is conventional inference is that the conventional inference tells you that there is a true value of the theta, and this lies within this interval with the confidence 95%. Nobody knows what that means, but everybody knows that this is not probability, because probability does not apply to statements which are true or false, and this can only be a true and false statements in the conventional framework. Because in the conventional framework there is a true value. Now what I'm telling you is that there is no true value. So if there is no true value, then what does this mean? Or what are we saying about these? So basically what we are saying is that this set of values of theta is reasonably well matched. If you take any value of theta inside this interval, you will get something which matches the data and cannot be rejected at the 5% level. If you take a value at the theta outside this, then that's strongly in conflict with the data. If you test this theta, you will find that the data is rejecting. So probably you don't want to use such a model. But it is important to note that the idea of true value has really hypnotized people. Since we know from the start that all models are false, so the fact that theta is not matched to the data on this is not grounds for rejecting the model. All models are false. So maybe it depends on the purpose, and we can that requires really much more knowledge of the real world application that you're doing. You might be willing to take a theta which is outside the 95% bounds, because the model this is not the primary purpose of the model. The purpose of the model lies in some other direction, and errors in the theta will not matter. This can happen. So since we know from the start that not all models are true, any models are never true, so the fact that the model fails in one direction is nothing surprising. All models will fail if you test them sufficiently. So the point is that, is it good enough for the purpose? And to answer that, you need to know what the purpose is. If you are doing quality control, if you are doing forecasting, whatever it is, it depends on what the purpose is, according to which you will judge whether you can use a theta which is acceptable, which is within the confidence interval or not.
इंटरवल पॉजिटिव वाली साइड हमने यहाँ थीटा को करना है सेपरेट, हम पैरामीटर को देखना चाहिए जो स्टैटिस्टिक हमें नहीं है,
Right.
तो यहाँ से जो हमने इंटरवल बनाया है इसका रिवर्स ऑर्डर में आएगा सर?
I don't understand.
सर वो पॉजिटिव वाला जो बैंड है करते तो हम ऐसे ही हैं, लेकिन सिंस थीटा हमारा नेगेटिव है हमने पॉजिटिव थीटा को कंसिडर किया है।
लोअर बाउंड
तो
T distribution is symmetric around 0. So theta minus A will also be T minus N minus 1.
x minus x bar bar mid
वो तो ठीक है सर। असल में ये प्रोबेबिलिटी स्टेटमेंट से हम स्टैटिस्टिक की वैल्यू निकालते हैं ना, जो हमने वो थीटा को सेपरेट किया है। तो यहाँ से ये जो वो S/n-1 है, इस फैक्टर को हम अगर वो इंटरवल बनाए तो हमारे पास
I have no idea what you're saying.
लेकिन चाहे कि इस पॉजिटिव साइड इस तरह नहीं चाहिए, हम उन्हें समझ नहीं आई, उनको समझ नहीं आता उनको तो मैंने कैलकुलेट सॉल्व करना है।
इनइक्वालिटी थीटा के साथ में आएगा ना।
Alright, so this is the conventional inference, and now we will study the Bayesian inference. Or this same model. So this is all. This is the for the driver. This is all you need to know. This 5 minutes we have covered everything that is necessary in order to do conventional inference. All of the material that previous was just to how that. In fact, I didn't prove the. I didn't study the conventional inference at all. I studied only the Bayesian inference. The conventional inference is also is similar but different. So you can get these details out of any book, but because this is the heart of conventional statistics, so this particular material is covered in detail in almost any statistical text, but not in econometrics, because econometrics we go more into more complex models, and that's a little bit unfortunate because all those more complex models are based on this simpler model. So now the next step is to look at the same model with the Bayesian framework. Now in this framework, it's useful to work simultaneously with two parameterizations. So I use n star to show that this is being parameterized by the precision parameter, and there's a data precision. Px is called the data precision, and Px is just 1 over sigma squared. Now, in the prior distribution, we say that theta given okay, so what was the theta as a prior mean? Yes, right. Theta given p theta is going to be a hyperparameter, the precision of the prior. This is normal with mean prior mean m and prior precision. So I'm going to use the star notation p theta, which is the same as normal with mean m and variance 1 over p theta. So this is the prior density of theta, which is conditional on the prior precision, and then the prior precision itself has the density of gamma, and this gamma can have k over 2 and lambda over 2. Oh, sorry. K over 2 and, yes, I think it is correct. Yes. So now, m, k, lambda, these are the prior parameters. These are actually called the hyperparameters. These p theta is not a hyperparameter because p theta is now I'm doing the full general case. Previously I was considering the first calculation I did, I assumed that variances were known. In that case p theta was a hyperparameter because it was assumed known. But now I'm considering the case where the variance is unknown in the original distribution, and therefore I'm going to put a distribution on the sigma squared also. The sigma squared itself will have a prior density. Sigma squared itself is Ig, yes. It's not p theta. It's px. Yes. It's no mistake. The data density px is gamma with parameter p theta. So there are two so sorry, I misspoke. Lambda is now p theta. So the hyperparameters are mk and p theta. We have two parameters, theta and sigma squared. In the Bayesian estimation, it's better to take the parameters to be theta and px. Now we put prior density on both of these parameters. So theta and px are both going to have a prior density. Theta is normal with mean m and variance equal to p theta. I think that's correct. And the variance sigma squared has a not the variance sigma squared. The way it is done in a conventional text, you will see that sigma squared has an inverse gamma distribution, and this is what's in the notes that you have. But if we instead of looking at sigma squared, we look at the precision, and the sigma squared is inverse gamma prior distribution, but the precision has a normal, any standard gamma density, and the gamma density has this form. Now, once you will put down the prior, so now where does this prior come from? There are two ways to generate the prior. One is to say that we take the uninformative prior, which is the calculation that we have already done last time. In the uninformative prior, then this p theta becomes infinity, so theta actually p theta precision becomes 0. The prior precision becomes 0, prior variance becomes infinity, so the density doesn't matter. The density is p theta equals 1, and the sigma squared is given the density which has log sigma squared is uniform, so it is equal to 1. So that also corresponds to the gamma with something like the scale parameter going to 0. P theta goes to 0. So in both of those cases you get, and then you get the posterior which we calculated. Now, so that's one density. The other density is that the other method is to say, okay, you start with this prior, the informative prior, and then you take a preliminary sample. And then you get the posterior for that preliminary sample, which is the same as we calculated. And now we take the second sample. And when you take the second sample, then you get to the true posterior. But now you take that preliminary sample, and you have your first prior. That is now an informative prior, and it will look like basically. So what people say is that you can think of this as an artificial sample. That the first sample is just imagine what a sample would look like, and so that will tell you how to set up a prior how to set up an informative prior for your problem. So once you have this prior, then you can calculate the posterior doing exactly the same steps that we did last time, except that they will be more complicated because instead of having you have the data density and you multiply it by the prior. The prior was very simple that time. It was 1 and 1. Actually d theta d sigma squared over sigma squared. Now it will be the data density will be exactly the same as before, but the prior density will also be a normal gamma and a complicated density. But it works very smoothly because these are natural conjugate priors. Automatically they mix well, and so I'm not going to do the calculations which are done in the notes that in almost any Bayesian text, but I have also attached one which does them fairly clearly, except for the one fact that it uses the inverse gamma instead of the gamma, which is the same. The calculations are the same. So now what we get, this is the crucial thing, that the posterior density of theta and p theta given the sample x1 to xn, this is the end result of the Bayesian calculation, and this contains everything that you need to know in order to do the inference. So this density is this is theta given p theta is normal. So let me use the n star notation. Basically, we want the joint density of theta and p theta conditional on the data. So that's the posterior density. But it's easier to express this joint density as the conditional density of theta given p theta and the marginal density of p theta. Both of these are conditional densities, and I haven't mentioned it specifically here, but the x's are being conditioned on here. So it's a double conditional. First we condition on data, then we condition on p theta, and we get the marginal density. Okay, so now this is normal, and the normal density has two means. The one mean is the data mean, which is A. This is what we would estimate theta to be using conventional inference. That's the center of the data, and that's the maximum likelihood estimate of theta. So based on data alone, we would use A. Based on the prior alone, we would use M. So now the posterior is going to combine these two pieces of information, and they will be combined according to the precisions. So this one receives the weight sigma squared over n, because that's the data density, and sigma squared over n, sigma the reverse of that. So that will be n times px, which is n over sigma squared, plus the prior, which is now p theta, and then these are weights, and then we divide by the sum of the weights to get the weighted average. So the posterior mean is a very natural object. He says take your prior information, the mean of that, and take the data information and combine them, but you can't take a simple average because the sample sizes are different. The prior sample may be a small one and the data sample may be a large, or vice versa. In any case, so you combine them, you give them the weights, and the weights are according to the precisions. The more precise the data is, the more the weight it gets, and the less precise, the smaller the weight it gets. So it's very natural, it's a weighted average. And now the variance, well, I've used the n star, so the precision is just the sum of the two. So this is the posterior density. It's very natural, and that you just add the two. What is the amount of precision that you have in your final inference? Well, it's the precision you got from the data and the precision you got from the prior. You just add the two together. It's like the prior is one sample and the precision and the data is another sample, and you just combine the two samples and you just get the sum of the two precisions. So it's very natural and easy to understand. One very important thing to note here is that as n goes to infinity, the prior will wash out. The weight of the prior will go to zero, regardless of how much. I mean, even if you start with a very big prior sample, as the data sample increases, the value of the prior will go to zero because the n will go to infinity. So the only thing you will have is a here, and the only thing you will have is n over sigma squared here in the precision. So you will have exactly the same distribution that you get in conventional inference. So it means that in large samples, conventional inference and Bayesian inference on theta will be exactly the same. So only in small samples can you have a difference. Another thing that is important is that if you put uninformative priors, then you are going to get the same inference as conventional. I just received a paper to referee for a journal recently, and the author was doing Bayesian inference, and he did a lot of complicated things, but basically what he did was he put an uninformative prior, and he said that in small samples Bayesian inference is better. This is true. In small samples Bayesian inference is better, but with an uninformative prior, his inference was exactly the same as the conventional inference, which he didn't realize. So in that paper, the Bayesian inference was just distraction. It didn't add anything of value to the inference, because if you put an uninformative prior, you're not going to get any difference from the conventional inference. Now the other thing, this is theta given p theta. P theta itself has a gamma density, and the gamma density has n minus 1 over 2 degrees of freedom, and it has a scale parameter which is equal to the s. That's very important. Yes, that's where I was having a problem. It's Yeah, I think that's what it is.
लास्ट लेक्चर में आपने S over 2 लिखा था और उसमें दोनों में डिफरेंस
नहीं, this is the correct one. अगर S over 2 लिखवाया था तो मैंने वो गलत लिखवाया. Where S is just summation I equals 1 to n xi minus x bar squared. So this is the all that we need. Remember that the posterior distribution depends on the data, but what we see is that it depends on the data only through A and S. And that's also the same thing, that this is what the sufficient statistic means. That if I want to make inference about theta and sigma squared from the data, all I need is the value of A and S. I don't need the specific individual values of the xi. So the sum of squares of deviations from the mean is S. From the sum of squares of deviations, I can get the value of the precision. This is the posterior distribution of theta. So I can find what is the range of values of sigma squared, or what is the range of values, the 95% credible interval. And similarly, I can find the values of theta conditional on theta. But this is not satisfactory, because theta itself, p theta itself, is random in the Bayesian inference. So we have to do one more step to get the marginal distribution of theta. So the marginal distribution of theta requires integrating theta out of this density, and that can be done. And what you do is you theta minus the value given x, which is the posterior mean, which is this expression over here. So you subtract the mean, and then you divide by the variance, which is the square root of the variance. And now this turns out to be t distribution with n minus 1 degrees of freedom. So now I can construct a confidence interval for my 95% credible interval for theta by looking at this density, and actually Tn minus 1 is a symmetric density, so I can find the limits. It will be like minus 2, yani if for large n it will be the same as the normal density. So between so this thing will lie between minus 2 and plus 2 with 95% probability, and this is a known number and this is a known number. So I will have a range of values of theta, that theta is between such and such number and such and such number with 95% probability. And in the Bayesian framework, this is actually a probability statement, that is, this is the probability of theta. But again, the interpretation of this that I am suggesting is not that we should take it as a probability, but each theta has a density. The density value is a measure of how well this is matched. So the 95% credible interval is the set of values of theta which are best matched to the data. These are so that's the interpretation, which is the same as the confidence interval interpretation. That these are the values of theta which are matching to the data. Now, this is all the calculations that we need for applications, and so now the next step is